Okay, so we are going to be doing implicit differentiation, which is section 5. So if you look at the implicit form versus the explicit form is what we have been taking the derivative of. You notice it's y equals, and we may have to rewrite them together. So if we were to do this derivative from here, and I know there's a derivative to the right, but using this form specifically, we would multiply the exponent in front, and then we would subtract from the exponent, and then we would rewrite it, and we would have this, and that matches up with the derivative on the other side. The implicit form is a little different. You can actually derive it from here, but y is a part of the product now, and so the derivative of y is dy over dx. So when we do that, we have to match it up accordingly. That's the derivative of y with respect to x. That's why we do that. So we'll have to product rule this. 1, so 1 and 2. 1d2, the derivative of y is dy over dx. It's 1 dy over dx, so the derivative of a variable with an exponent of 1 is just 1. Okay, so 1d2 plus 2 d1, and the derivative of x is equal to 1, and the derivative of 1 is equal to 0. So we have this. So it looks goofy, but if I were to simplify this and solve this, I would be able to get the correct answer. So that when I do this, I will have dy over dx is equal to subtract the y and divide by x. Well, that doesn't look anything like the other one we have, except the fact that we know that y is equal to 1 over x if I were to solve that for y. So then I actually go plug that in, negative 1 over x divided by x, which is negative 1 over x squared. So obviously that's a long way to do it in this specific case, but that would be the implicit form, and that would be the explicit form. So we're going to practice implicit differentiation because we've been doing explicit differentiation, and sometimes implicit differentiation is easier. Okay, so some of these may require that, some of them won't. We're just going to evaluate and practice. The derivative with respect to x of x cubed is just going to be 3x squared. Okay, and then the derivative of y cubed is going to be 3y squared dy over dx. Okay, one of the reasons you write that is technically this is dx over dx, but dx over dx, that's all 1, so it's 3x squared. So we haven't been writing that because we didn't need to write it, but with y, we do need to write it. All right, this one, the derivative of x is just 1, but the derivative of 3y is 3 times 1 dy over dx. Again, anytime you derive y, you're going to have the dy over dx. This one is a product rule, so we're going to do 1 d2 dy over dx plus 2 d1. Only when you take that derivative, that needs to be a 1, do you have to do that. And it didn't say to simplify or anything like that, so you can just leave it like that. So guidelines for implicit differentiation, I've kind of told you about them, but you're going to differentiate both sides of the equation with respect to x. Then you want to get dy over dx by itself. It's not wanting you to leave it, it's wanting you to solve for dy over dx. Like if I'm asking you, find dy over dx, but my y is kind of sprinkled in there, your end thing should be dy over dx equals. So you'll have to solve for dy over dx. Okay, that's our goal. So you may have to group things together, factor dy over dx out, and then solve for dy over dx. So we'll just, again, it's one of those things that take some practice. So we'll just do this one. So we're going to derive each part. So the derivative of y cubed is 3y squared, just like it is when we do x, but we have to do our dy over dx, plus 2y dy over dx, minus 5 dy over dx, minus 2x. You could write dx over dx, but it would simplify to 1, and the derivative of negative 4 is just 0. So when it's saying, it's wanting you to get everything that has dy over dx on one side and everything that does on the other. So I'm going to move this 2x, he's the only thing that doesn't have one, to the other side. So that I have 3y squared dy over dx plus 2y dy over dx minus 5 dy over dx equals 2x. Then if you notice, all three of these terms have dy over dx. I can actually factor dy over dx out. And I'm, didn't mean to put an equal sign. And I will have 3y squared plus 2y minus 5 equals 2x. Then I will divide both sides by 3y squared plus 2y minus 5 all over 3y squared plus 2y minus 5. So dy over dx is equal to the quotient 2x divided by 3y squared plus 2y minus 5. So if we would have done that explicitly, you would have had to solve for y, which would have been nearly impossible with this function. If you look at the original function, y cubed plus y squared minus 5y minus x squared equals negative 4, how would you have solved for y? It's not a quadratic. It doesn't have all this other stuff. And so it would be much. Okay. We're going to do a similar thing. We're just going to add to it. So we're determining the slope of the tangent, which is just the derivative, but it's at a given point. So instead of having x's and y's, we would be plugging in the root 2 and negative 1 over root 2. Okay, so we're still doing the same thing. So just a reminder that slope is change in y over change in x, which is dy over dx. So that's our goal. So we'll look at our function. It's x squared plus 4y squared equals 4. The derivative of x squared is just 2x. The derivative of 4y squared is 8y dy over dx. And the derivative of 4 is 0. So then I want to solve for dy over dx so that I have my slope isolated. So I'll subtract 2x from both sides. So I have 8y dy over dx equals negative 2x. I'll divide both sides by 8y. So I have my slope equation, dy over dx, is equal to negative x over 4y. I simplified the 2 and the 8. Okay, so that is our slope. Okay, but it wants it at a specific instance. So at the ordered pair root 2, comma, negative 1 over root 2. Really, they probably should have rationalized that, but they didn't. That's okay. We'll rationalize anything we get, and I'm just going to plug those values in. So my slope is equal to negative x, in this case, root 2, all over 4 times y, which is negative 1, over root 2. Okay. I have a negative in the top and a negative in the bottom, so I'll get rid of those. And then I am going to kind of think about it like this first, and then that fraction, the 1 over root 2, if you're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So I can actually do it more like this. Okay. And I would have 2 over 4, which is 1/2. Okay, next one. Determine the slope of the graph at the point. So we're doing the same thing. So we're still looking for dy over dx. Okay, determine the slope of the graph. So we're going to, and if you look, your x's and y's really are intermingled here. So we will definitely need implicit differentiation. Where on the previous one, we might have been able to do it without implicit differentiation. We would not be able to do it in this case. Okay, so we'll do our derivative. I'm going to rewrite it over here. I like to do my work underneath my function. Okay, so we have to chain rule that left side. So I will have 6 x squared plus y squared to the first power. So that's a chain rule, derivative of the outside. And then times the derivative of the inside. So 2x plus 2y dy over dx. Whenever you derive that y term, we haven't derived a y term just yet in that problem. Okay, derivative of the outside times derivative of the inside. So that derivative is done, equal to, and we'll have to product rule this. I'm going to group 100x together. So I'm going to do 1 d2, and the derivative of y is just dy over dx, plus 2 d1, and the derivative of 100x is just 100. So I'll kind of squeeze that in there. So I have this big, ugly thing here. All right, and so what we can do is we need to figure out a way to solve for dy over dx. So I would say let's FOIL the left-hand side, and we need to put our dy over dx's on the same side as each other. So I'm going to have I'm going to do 6. I'm going to think of this already multiplied too. So 6x squared and 6y squared so that I can save myself some trouble. So actually, we will have first, which will be 12x cubed. Outer will be 12xy dy over dx. Inner will be 12 y squared x, or actually I prefer to write them in alphabetical order, xy squared. And then first, outer, inner, and then last we will have 12 y cubed dy over dx equal to 100x dy over dx plus 100y. Okay, so I have this term, and this term, and I would like them all grouped together, and I would like everything else. So I'm going to do this all one time. So I'm going to move my 100x dy over dx to the left, and I'm going to move my 2x cubed and my 12xy squared to the right. Okay, so that I have 12xy dy over dx plus 12y cubed dy over dx minus 100x dy over dx equals 100y minus the 12x cubed minus the 12xy squared. Okay, so we just move those around. Then I can factor out the dy over dx from the left side. And I have 2xy plus 12y cubed minus 100x equals to 100y minus 12x cubed minus 12xy squared. And then I will divide by this whole thing to both sides. And this does simplify a little bit. If you notice, all the terms are even. Not just even, but divisible by 4. So we can simplify it just a little bit by dividing everything by 4. So that I have 25y minus 3x cubed minus 3xy squared all over 3xy plus 12. Oops, sorry. Need to erase that. Make that a 3y cubed minus 25x. So we've simplified that. Now where it gets a little bit bigger is we are going to have to plug in. So I won't write out the plug-in part just because I don't have the space to, but we have to plug in 3 for x, and we will have to plug in 1 for y. So everywhere there's an x, I'm going to put that value, and everywhere there's a y, I'm going to put the other value. And so then when I do that, I will get 13/9, okay, as your answer. All right, so we are going to, and that is our slope because it did ask for our slope. We are going to find dy over dx implicitly for this function. So you notice y is kind of trapped in sign. That's why we have to do it implicitly. Because if we were to solve this for y, we would end up using inverse functions, and we don't have the background to do derivatives on inverse functions. You will by the end of the chapter, but we're not there yet. So it'll save you a little bit of trouble. All right, so what I want to do is a derivative of sine y would be cosine, right? Y, but since I'm deriving y, I have dy over dx. And the derivative of x is just 1. And so then I will divide by cosine y, divide by cosine y. And that would result in dy over dx is equal to 1 over cosine y. You could, if you wanted to rewrite that, that is secant y. But you could leave it as 1 over cosine y. That would be okay. All right, so here's another one. So the reason we can't, one, it's asking for the second derivative. I kind of cut off the top of that too. So we have to derive twice, but you can't explicitly derive this because if you were to solve for y, and this looks like an inequality to me, but it's not, you would end up having 2 functions because to solve this for y, you have to end up square rooting both sides. So you're going to have a positive square root of 25 minus x squared and a negative square root of 25 minus x squared. So you're going to have to do things twice. So it's not a connected situation. So if we do it implicitly, we can. So the derivative, first derivative, is 2x plus 2y dy over dx equals 0. Derive it again. And then we'll have 2 plus, now this is where it does get a little different. When you do this, you have to be careful because you have some strange things going on. So actually, before we differentiate it the second time, we need to solve for dy over dx. We can't do the second derivative. We can't do it as it is there. I was jumping the gun a little bit there. So let's solve this for dy over dx so that then we can do the second derivative. So I will subtract 2x to the other side so that I have 2y dy over dx is equal to negative 2x. And then I'll divide both sides by 2y, and I will end up with my first derivative being negative x over y. So I have this. Now moving on to second derivative, we'll have to do the quotient rule. So we will do low d high minus high d low all over the square of what's below. So we'll do low d high minus high d low, derivative of y is dy over dx, all over the square of what's below. So we have this. And I can simplify that a little bit to negative y plus x dy over dx over y squared. Some might think that's a good place to stop, but it's not. You don't want to have dy over dx in your second derivative. It needs to be completely solved. But we know what dy over dx is. It is this. So all we have to do is plug that in place. So we'll have negative y plus x times negative x over y. So I just substituted in what it's equivalent to all over y squared. And I can simplify that. So I have negative y plus, actually we'll change it to a minus since we are subtracting. So it's got that negative that you're multiplying by minus x squared over y all over y squared. You wouldn't leave a fraction, so we'd have to get a common denominator. The common denominator of this guy is currently 1. So I'll multiply top and bottom by y so that it's the same, and so that I will have negative y squared minus x squared on that numerator, and then the bottom is y, and then the next bottom is y squared. So if you think of this as a fraction, so you have negative y squared minus x squared over y as your top, and y squared over 1 as your bottom, you would multiply by the reciprocal. Instead of dividing by y squared, you'll multiply by 1 over y squared. And that leaves you with negative y squared minus x squared all over y cubed. Now, to make it a little more exciting, is if you can actually simplify it a little bit more. If you notice in the top how they're both negative, I can actually factor out that negative. So I'll just pull it entirely outside of it. And y squared plus x squared, we actually know what that's equivalent to. This is the same as this. Did you see that? So then I can actually have negative 25 all over y cubed. Okay. So second derivatives require a lot more work, but you do a lot of substituting sometimes, and it works out. All right, so here's a big problem. They gave us a graph. We're just going to find the tangent line to that point they gave us, and they drew a picture of the tangent line for us. We just have to actually find the equation of a line. So we're doing one step more. So you're not just finding your slope, you're also finding the equation of your tangent line. So first off, I think it would most likely be simpler if we were to distribute that x squared through here so that we had x to the fourth plus x squared y squared equals y squared. And then we can derive it. We have 4x cubed. We will have to product rule this x squared y squared, so we'll do 1 d2 plus 2 d1 equals, and then the derivative of y squared is 2y dy over dx. All right, so we do need to get our dy over dx's together, and I'm going to subtract this whole term over to the right so that I have 4x cubed plus y 2y squared x. If I were to, let me write that a little bit better, simplify that a little bit, plus 2xy squared equal to, and I'm going to factor this out as I go. If you can get into habits of doing that, you don't have to do as much work. Okay? So if you notice, I went ahead and took out the dy over dx that both terms had. So it's still this 2y term, but I factored the dy over dx, and it's still this 2y and x squared term, but I factored the 2 out. Okay? And then I'll divide both sides by 2y to x squared y. And if you notice, everything is divisible by 2. So whenever we use it, we should simplify that. So we'll do 2x cubed plus x squared y all over 2, nope, factoring a 2 out and canceling it, y plus x squared y. Okay, and we can't simplify that yet. Yes, there's x's on top. Yes, there's y's on bottom, but there's not the same number of them in all parts. So the top has 2 x's and 1 y, and the bottom has at max kind of thing, but both terms don't have the y. In the bottom, both terms have y, but both terms don't have an x. So there's nothing to cancel. So that is the equation of our slope. So then we need to go plug in our root 2 over 2, root 2 over 2, and simplify that. Okay, so that we'll have it. So we will have 2 root 2 over 2 cubed plus root 2 over 2 squared times root 2 over 2 all over root 2 over 2 plus root 2 over 2 squared times root 2 over 2. So that's crazy. And then we simplify that a little bit more. We will have 2 on the top. Root 2 cubed is actually going to be like root 2 squared times 2. Okay, so you're going to have 3 of them. So on the top of this fraction, you'll have 2 root 2, but the bottom will now be 8 because 2 cubed is 8. So then the next one we'll have 2 over 4 and then root 2 over 2. And on the bottom, we will have root 2 over 2 plus 2 over 4 root 2 over 2. So all that craziness, and we'll be able to simplify it. If you notice, all terms now have a root 2 over 2. Okay, so I could actually simplify by factoring, canceling out. Let me change colors, actually. I thought I did. All right, so that guy, this guy, and there's a 2 in this, multiplication-wise, and we'll simplify all that. So then I am left with 2 times 2 over 4 plus 2 over 4 divided by 1, because that entire thing canceled, plus 2 over 4. And so now it's pretty simple. This is 4 over 4 when you put it together, so that's going to be 1. So we have 1 plus 1 half, so we have 3 halves on top. And then the bottom is also hold on, I think we were supposed to have a minus somewhere. Where did my negative go, guys? We lost it. This is supposed to be a negative. A negative. A negative. And a negative. Okay. And you'll end up with 3 for your dy over dx. Okay. All right, so then you have to do y minus y equals mx minus x, if you remember that from algebra, and we reviewed it. So we will use our slope as 3, but then we'll have to plug in our ordered pairs. Okay? And you can leave it like that. It doesn't preference what form of the equation. Now, if they wanted it in point slope form, you would have to solve for, or they wanted it in slope intercept form, you have to solve for y. All right. So sometimes it's convenient to use logarithms to help you differentiate. It has its own name called logarithmic differentiation. And what it does is it kind of frees up some of your space. So if you look at the problem to the left, that is a chain rule on top, a chain rule on bottom, and it's a quotient. So when you did your low D high, you'd have to chain rule, plus your high D low, you'd have to chain rule, and then you'd have the bottom. So what logarithmic differentiation does is it kind of frees up some of those processes that you might have to do. The only reason it gives this domain, by the way, is to make it exist. So x can't be 2, otherwise you would end up with some domain issues, okay, for what we're getting ready to do. All right. So because we're going to take log of both sides, you can't have log of 2. So logarithmic differentiation starts with the process of taking the natural log of both sides. Okay, in doing so, you can use your log rules to rewrite the side on the right to make it simpler. So we'll keep the natural log of y on the right, but on this one, I can rewrite my numerator if the power goes out front, and the numerator is here. You subtract what you divided by, the power goes out front, and I have this, okay? And so now I can do the derivative. The natural log of y derivative, if you remember, we just learned that in last section. The derivative of natural log is 1 over what's inside the function, and then you might have to chain rule past that. So it is 1 over y. And you derived y, so dy over dx equals, okay, the derivative of natural log again is 1 over. That 2 is still up front if you want, or you can put it in the numerator, and the derivative of the bottom is just 1, so you would multiply by 1, but I'm not going to write that. And then minus 1/2, and natural log's derivative is that, and this one does have to chain rule. The derivative of the inside is 2x. Okay, so we can simplify that a little bit. So I have 1 over y, dy over dx equals 2 over x minus 2. This 1/2 and this 2 simplify, minus x all over x squared plus 1. So we have this, all right? And then we need dy over dx solve for itself, so I will multiply both sides by y, so I can move the y to the right. And then at the same time, I will also need to combine my my fractions. So we'll need a common denominator. They're going to need each other, so I multiply top and bottom of this by x minus 2, and I multiply top and bottom by this by x squared plus 1. So that I have dy over dx is equal to 2x squared plus 2, if I distribute that, minus x squared plus 2x, if I distribute that, all over, and I am not distributing this, x squared plus 1 and x minus 2. And then don't forget, I multiply that y over to the other side, so it's dy over dx by itself. Let's go ahead and combine like terms in the top. Again, I would not, and this time I know what y is. I'm going to plug that in. Okay, you don't have to simplify it past that, but I will plug in y. So if I combine my x's on top, I'll have x squared plus 2x plus 2 in parentheses all over the x squared plus 1, x minus 2. And I'm going to continue this fraction bar because I'm going to multiply by my y. So on the top, I'm going to have x squared minus 2 squared, and on bottom I'm going to have square root of x squared plus 1. So I have this crazy thing, and there actually is a little bit you can simplify. If you notice, I have a multiplied x minus 2 on bottom and a multiplied x minus 2 on top, so that'll make that power 1. And then also this and this are considered like terms, with the right one having a 1/2 power. So when I rewrite this, I will have x squared plus 2x plus 2 times x squared minus 2, just one of them because we canceled one out of the bottom. And then I'll have x squared plus 1. This guy has a power of 1. That guy has a power of 1/2 with the square root, so it's 3/2. And you can leave it like that. Okay, you can leave it like that. And this doesn't have a squared. I don't know where I got that. Okay. All right, last example. So this one's really interesting because there are a couple different ways to do it. But if you notice, you can't just use your regular exponential rules because your base is not a number. So normally we would have like 5 to the 2x. Well, then you could use an exponential rule. But your exponent is a variable and your base is a variable. So logarithmic differentiation is definitely the way to go when your variable's in two very different locations. So I will natural log both sides. And why that's helpful is because I can rewrite the right-hand side. Exponents come down in front for logs, like this. Well, now it's just a product. So when I derive both sides, I'll have 1 over y, dy over dx, equals 1 d2 plus 2 d1. And I'll simplify. And I have 2x over x, so it's just 2, plus 2 natural log of x. And I have my 1 over y, dy over dx. But I do need to have just dy over dx. So I'm going to multiply both sides by y, just like we did on the last problem. So dy over dx is equal to, and sometimes you can leave it like that if you don't have your y solved for. In this case, we have our y solved for, so it's not that hard to multiply it there. And we can also factor out a 2. So I'm going to pull out the 2, okay? And then I have my y, which is x to the 2x, and then I have that parenthesis thing with the 2 factored out. Order is kind of relative on how you write multiplication, but in general, if you put your bigger parentheses to the right, it's easier to read and use. And that is done.